Hello, and welcome to our discussion of some applications of the generalized Cauchy integral formula. We'll begin by looking at the function f of z equals 1 divided by 1 plus z squared, and we'll find a power series for f centered at z equals 0, and the largest positive number r, such that the power series converges on the open ball centered at 0 of radius r. So begin by observing that if z is a complex number whose modulus is less than 1, then the modulus of the number z squared is equal to the modulus of z squared. Now, because the modulus of z is less than 1, its square is also less than 1. And so the geometric series tells us the following. F of z, which we can rewrite as 1 divided by 1 minus negative z squared, is going to be the sum from k equals 0 to infinity of negative z squared raised to the power k, and that, of course, is the sum from k equals 0 to infinity of minus 1 to the k times z to the 2k. So we have a power series representation for f when the modulus of z is less than 1. That is, we know the power series converges on the open ball centered at 0 of radius 1. Now, what happens if the modulus of z is greater than or equal to 1? We'll use the good old test for divergence. We begin by looking at the case when the modulus of z is exactly equal to 1. And then we have the following. The limit as k goes to infinity of the modulus of minus 1 to the k times z to the 2k is the limit as k goes to infinity of the modulus of z raised to the power 2k. And that's the limit as k goes to infinity of 1, which of course is not 0. And so by the test for divergence, the series cannot converge when the modulus of z is equal to 1. And if the modulus of z is strictly greater than 1, then the limit as k goes to infinity of the modulus of minus 1 to the k times z to the 2k is again equal to the limit as k goes to infinity of the modulus of z raised to the 2k, and that's going to be equal to infinity because the modulus of z is strictly greater than 1. So in both cases, the test for divergence says the series will not converge. We can look at this another way. Our function is f of z equals 1 over 1 divided by 1 plus z squared. And we note that this is not going to be defined at z equals plus or minus I, because then we would be dividing by 0. Otherwise, f is defined on the whole complex plane. And so f is not defined at z equals plus or minus I, and f therefore isn't analytic at plus or minus I. There's no way to make f analytic at plus or minus I. So if we look at a picture here, in blue dashed line, I've drawn the circle of radius 1 centered at the origin. And we see smack on the boundary of that circle are the points plus or minus I. So as soon as I try to push this power series representation beyond the ball of radius 1 centered at 0, I'm going to hit plus I and minus I. And not only will the power series not converge at plus or minus I, the function itself doesn't extend to be analytic at plus or minus I. Here's another example. Let's say we look at a polynomial of degree n. So this is a function p of z, which will be the sum from k equals 0 to n of some numbers ak times powers of z, z to the k. And it's a polynomial of degree n. That means that we're assuming an is non-zero. And I claim the following. If you give me a point z0 in the complex plane, I can rewrite p in the following form. P of z will be the sum from k equals 0 to n, again, but now of some coefficients bk times z minus c0 raised to the power k, where here these coefficients b0 up through bn are complex numbers that may not have anything to do with a. So how can we go between these two representations of a polynomial? One sort of centered at 0, the other sort of centered at an arbitrary point, z0. So first, p is an entire function. What is p? It's just a sum of powers of z, and we know that positive powers of z are differentiable functions by the power rule. So p is entire, and it's holomorphic, therefore, on an open set containing the closed ball centered at z0 of radius 1. Specifically, that open set can be the entire complex plane. And so p has a power series representation at this point z0. We can write p of z is the sum from k equals 0 to infinity of some coefficients bk times z minus z0 to the power k. And specifically, we know that bk is equal to the kth derivative of p at z0 divided by k factorial. And this power series representation is ostensibly valid for all points z in the open ball centered at z0 of radius 1. And I'm picking the radius to be 1 just for convenience. We'll do something with the radius in a moment. But what do we know about polynomials? If you differentiate a polynomial enough times, you get back 0. Specifically, since p is a polynomial of degree n, if you differentiate p n plus 1 times or more, you get the identically 0 function. That is, if k is greater than or equal to n plus 1, then the kth derivative of p at any number z is equal to 0. And so this means that the bk's eventually are going to be 0. And therefore, we have p of z as the sum from k equals 0 to n of bk times z minus z0 to the power k for z in this open ball, because bn plus 1, bn plus 2, and so on are all 0. But it seems that my representation is only valid for z in this ball of radius 1 around z0, and I want to get this representation to hold for all complex numbers z. So here's what we can do. It's a very artificial restriction to z equal to the radius being 1. So now let your radius be some positive number. Then, if the radius is some positive number r, p is still going to be holomorphic on an open set containing the closed ball centered at z0 of radius r. This open set, of course, is the complex plane. And why is this sentence true? Because p is entire. P is differentiable on the whole plane. So what does this mean? We still have the power series representation p of z equals the sum from k equals 0 to infinity of the kth derivative of p at z0 divided by k factorial times z minus z0 to the k for z in the ball of radius r centered at z0. And once again, this power series representation just collapses to the finite sum from k equals 0 to n, because for higher derivatives, k equals n plus 1, n plus 2, and so on, the kth derivative is going to be 0. And so this representation has to be true really for all numbers r greater than 0. So no matter what z I pick in the complex plane, eventually that z will be contained in some ball centered at z0 of radius r. Just blow up the ball, make it really big. And so I have this representation of p of z as a finite sum of powers of z minus z0. And for our third and final example, we're just going to calculate a line integral that would be difficult, if not impossible, to do via the definition of the line integral. So we'll evaluate the integral over the circle modulus of z is equal to 3 of e to the minus z divided by z cubed. So this is, of course, the circle centered at the origin of radius 3. And this is in a video about the generalized Cauchy integral formula, so you probably want to use that. We'll put f of z equal to e to the minus z. This is an entire function. And so let's call the integral I. Then I will be the integral over the circle modulus of z equals 3 of f of z divided by z minus 0 raised to the power 2 plus 1. So my idea here is that I want to rewrite the integral and the integrand in such a way that I see the generalized Cauchy integral formula basically popping out. So I always want some differentiable function in the numerator, that's f, and in the denominator, z minus a constant raised to some power 2 plus 1. You always want a 2 plus 1 in that power in the denominator. Now we know if I had one extra factor here, what the integral would be. 1 over 2 pi I times the integral over the circle modulus of z equals 3 of f of z divided by z minus z0 raised to the power 2 plus 1. That whole product is equal to f double prime of 0 divided by 2 factorial. And if I differentiate f twice and evaluate it at 0, I get minus 1 squared times e to the minus 0 over 2, and that is 1/2. So all I have to do is multiply through by 2 pi I to clean things up, and I get the full integral I is equal to 2 pi I times 1/2, which is, of course, pi times I.